Hello, and thanks for using TickBoom. This video is a follow-up to a prior video where I worked through a solution for part 5 of this question. So it's been quite the journey to get here. About a month ago, I released some videos where I worked through part 1, 2, 3, and 4. I then had a bit of a struggle with part 5, and it wasn't immediately clear to me how to tackle the question. Then with the assistance of some people, I was able to get my head around a solution. And that solution is what I've just worked through in a prior video. But part of that solution involved making an assumption that I said I would then go and prove separately. So this video is about proving that the assumption I made in working out the solution to part 5 is actually a valid assumption, and therefore the conclusions that we made in that proof are robust and can be depended on. So basically, just to remind ourselves, what we did in part 5 is that we proved that the limit as n goes to infinity of x1 plus x2 all the way up to xn over n to the 2/3, we proved that that limit is equal to the cubed root of 9 on 2. And in doing that, we had to assume that there was some value k which was equal to the limit as n goes to infinity of xn n minus 1 to the 3rd. So we made that assumption, and then in making that assumption we were able to then go through, solve for k, and get to this ultimate result. But in order for that whole solution to be valid, we needed to first prove that k existed. And that's what I'm going to do now. And what we can use to help with this is something called the Monotone Convergence theorem. Now, according to this theorem, if you have a function that is bounded above and is increasing, then it must have a limit. So that's kind of the approach we're going to take. Now, before we actually get there, there is a preliminary step that we can do that will help us, because finding the limit of this particular function is quite a challenging task, and actually we can find the limit of a similar but slightly different function that then can get us to what we need. And so what I'll do to start is, let's just say, or let's show that the limit as n goes to infinity of n minus 1 on n minus 2 to the power of a third. Now that limit we can see would just be infinity on infinity to the third, which would just equal 1. So what that means is that the limit as n goes to infinity of, and if I just multiply top and bottom by xn, and then we'll have n minus 1 to the third, n minus 2 to the third. That's also going to equal 1 because I haven't changed anything. So therefore, what we can say is that the limit as n goes to infinity of xn n minus 1 to the third is equal to the limit as n goes to infinity of xn n minus 2 to the third. So what that means is that if I can find the, or if I can prove that this limit exists, then I've also proved that this limit exists because they're both equal. And so in this video I'm going to go about proving that this limit exists because it's a bit of an easier task. So as I mentioned, according to monotone convergence theorem, I need two things. I need to show first that the function is bounded and that it's increasing. So if I start by asking the question, is it bounded above? Well, from part 1 of the question, the result that we had to prove there was that xn is less than or equal to 1 on the cubed root of n minus 1. So therefore, xn n minus 1 to the third, just bringing that up, must be less than or equal to 1. And therefore, xn n minus 2 to the third must also be less than or equal to 1. Oops, sorry, less than or equal to 1. Since we know that xn n minus 2 to the third must be less than xn n minus 1 to the third, because I'm subtracting more here. So from there, from that result in part 1, we can quite easily show that therefore xn n minus 2 to the third is bounded above. It's bounded by 1, so it won't ever go higher than 1. So now we have to ask the question, is it monotonic increasing? And what that means is that as you increase n, the value of the function increases. So what it would really mean is that xn n minus 2 to the third would be less than xn plus 1, so I just move n plus 1 in the sequence, times n plus 1 minus 2, or n minus 1 to the third. So that's what we need to be true. So we can just rearrange. We'll get xn on xn plus 1 needs to be less than n minus 1 on n minus 2 to the third. And that's basically the same as writing that it needs to be less than 1 plus 1 on n minus 2 to the third. Those are equivalent things. You can see if you did n minus 2 plus 1 over n minus 2, you get n minus 1 on n minus 2. So those two are equivalent. So really, if we want to show that the function we're concerned about here is monotonic increasing, we need to show xn on xn plus 1 is less than 1 plus 1 on n minus 2 to the third. So that is our task. If we can do that, then we proved that this limit exists, which means the limit of what we really care about, what we depended on in the solution to part 5, that limit exists, and which means everything we did in that solution was valid. So if I just turn over, as a preliminary step, I'm just going to show a result that's going to come in handy, and it starts from pretty much the definition of xn plus 1. So we know 1 on xn plus 1 is equal to x1 squared plus x2 squared all the way up to xn squared. That was pretty much the definition of the recurring sequence, albeit inverted. So we also know 1 on xn would equal x1 squared plus x2 squared up to xn minus 1 squared. So that means we can say 1 on xn plus 1 minus 1 on xn would be equal to, you'd just be left with this xn squared. So that means 1 on xn plus 1 is equal to xn squared plus 1 on xn, which is equal to, if I factor out 1 on xn, you'd get the 1 plus xn cubed. And so now if I bring the xn up, we get xn on xn plus 1 is equal to 1 plus xn cubed. And that's going to come in handy because what we can now say is xn on xn plus 1 will be less than what we're trying to show, 1 plus 1 on n minus 2 to the third. That will be true if 1 plus xn cubed is less than 1 plus 1 on n minus 2 to the third. So now this has now become our task. This is what we want to show. Now, as a preliminary step, what I'm going to do is I'm going to prove, I'm just going to hone in on the xn cubed here, and I'm going to prove that xn cubed is less than 1 on 3 n minus 1. Because if I can prove that, that's going to then provide me with the foundation to then prove that 1 plus xn cubed is less than this here. So, and I'll do that for n greater than or equal to 3, and I'm going to use induction to do that. So what I'll do is I'll work through the steps of induction now. So the first step will be to show that it's true for n is equal to 3, the first value that I want to show this for. So in this case, the left-hand side would be equal to x3 cubed, and that would be equal to, just over here, if you remember, x1 is equal to 1, so x2 would equal to 1 on 1 squared, which equals 1. So x3 would equal 1 on 1 squared plus 1 squared, which would be a half. So x3 cubed is a half cubed, which equals 1 on 8. So that's the left-hand side. The right-hand side would equal 1 on 3 times 3 minus 1, or 3 times 2, which equals 1 on 6. Therefore, 1 on 8 is less than 1 on 6, so the left-hand side is less than the right-hand side, which means it's true for n is equal to 3. So step 2 of the induction is to assume true for n is equal to k, some value k. So what that means is we're assuming that xk cubed is less than 1 on 3k minus 1. And now what we need to do, and I'll just turn over, step 3, often the hardest part of any induction, is to show that it's true for n is equal to k plus 1. So really what that means is we want to show that xk plus 1 cubed is less than 1 on 3k plus 1 minus 1. So the ones will cancel there. So we need to show that xk plus 1 cubed is less than 1 on 3k. That's what we need to show. Now to do that, I'm going to first define a function zn. So let's let zn equal simply what we're focused on, the xn cubed. Now, if we think about what zn plus 1 would be, that's going to be xn plus 1 cubed. And if we remember what I just proved here, this preliminary result, if we rearrange for xn plus 1, what we'll get is xn divided by 1 plus xn cubed, and that's all cubed. So that's equal to xn cubed over 1 plus xn cubed, all cubed. Now if we think about what Zn was, what we defined it as, we can actually write that as Zn on 1 plus Zn, all cubed. So we've got this kind of recurrence relationship here between Zn plus 1 and Zn. And now if we define some function f of u, and we call that u on 1 plus u cubed, then we can see that Zn plus 1 is simply equal to f of Zn, since wherever there's a u, if we put a Zn, we get the result for Zn plus 1. So that's something that will come in handy as we try and work through this third step of the induction. Now to help us on this, let's consider our function f, but for a specific value 1 on j. And let's see what we can conclude about f of 1 on j. So if I just insert 1 on j wherever you'd put u, so you get 1 on j on 1 plus 1 on j cubed, which would be 1 on j times, and what I'll do is I'll write this part of the denominator 1 plus 1 on j times 1 plus 1 on j squared. And we can simplify that. The j times this first j plus 1 on j would become j plus 1. And the 1 plus 1 on j squared would be the first one squared plus twice the product, so 2 on j plus the last one squared. So it's 1 over all of that. Now if I expand this again, we'd get 1 over j plus 2 plus 1 on j plus 1 plus 2 on j plus 1 on j squared, so 1 over all that. And that really we can write as equal to, and we'll get j plus 2 plus 1, so j plus 3 plus 3 on j plus 1 on j squared. So that's what we can say about this f of 1 on j. Now, just turning over, what we can therefore say is that f of 1 on j must be, well, I'll just rewrite on this page what we had. It's equal to 1 on j plus 3 plus 3 on j plus 1 on j squared, which means if I only divide by this, if I only divide by a smaller amount, 1 over that would be bigger. So therefore f of 1 on j must be less than 1 on j plus 3 by itself. So that's going to come in handy for our induction. So when we have f in our function, the function of u that we just defined here, when we have 1 over something in the function, we know that the result will be less than 1 over j plus 3. Alright, so from step 2 of our induction, we know that z to the k, so let's see in step 2, so xk cubed, well we know xk cubed is less than 1 on 3k minus 1, and now remember that we defined zn as xn cubed, so that means xk cubed is just z to the k is less than 1 on 3k minus 1. So now if we take our function of both sides, we'll get f of zk is less than f of 1 on 3k minus 1. And now we've got f of 1 over something, so we can know that this will be less than 1 on, and here our j is effectively 3k minus 1, so we get 3k minus 1 plus 3, which means it's less than 1 on 3k minus 3 plus 3, and they'll cancel, which means it's less than 1 on 3k. Okay, so we know f of zk is less than 1 on 3k, and remember we showed that zn plus 1 is equal to f of zn, which means f of zk would be zk plus 1. Therefore zk plus 1 is less than 1 on 3k as required. That's what we had to show for step 3. So remember we had to show true for n equals k plus 1, which effectively meant we had to show xk plus 1 cubed is less than 1 on 3k. We've shown that zk plus 1 is less than 1 on 3k. Zk plus 1 would be the same as x k plus 1 cubed. So I'll just write that to make it clear. Xk plus 1 cubed is less than 1 on 3k. So that's what we had to show. That's what we have just shown. So therefore, by induction, we can conclude that what we were trying to prove, xn cubed is less than 1 on 3 n minus 1 for n greater than or equal to 3. Alright, so that was our preliminary step. Now what we can conclude, and I might just turn over here. So we can come back to our definition. We know xn on xn plus 1. We showed earlier that was equal to 1 plus xn cubed. We've just shown that xn cubed is less than 1 on 3n minus 1. So that means xn on xn plus 1 must be less than 1 plus 1 on 3n minus 1. So we've shown that. Now what that means is xn on xn plus 1 will be less than what we really want to show, which you may remember. What we really want to show is that it's less than 1 plus 1 on n minus 2 to the third. Xn on xn plus 1 will be less than that if we can show that 1 on 3 n minus 1 is less than 1 plus 1 on n minus 2 to the third. Because if xn on xn plus 1 is less than this, 1 plus, if xn on xn plus 1 is less than this, and if this is less than this, then it must be that xn plus 1 must be less than what we really care about. So now our task has become to show this. Can we show this result? If so, then we're where we need to be. So what I'll do to help with this is I'll do a substitution. Let's let m equal n minus 1. And if we do that, then really what we want to show is that 1 plus 1 on 3m is less than 1 plus 1 on n minus 2 would be m minus 1 to the third. So can we show this somehow? What I'll do is I'll cube both sides, so we'll get 1 plus 1 on 3m cubed is less than 1 plus 1 on m minus 1. And now if I focus on this left hand side and we use the binomial expansion, which you would have seen in my prior video where we were working through step 5, we know that 1 plus x to the n can be rewritten as the sum from r equals 0 to n of ncr x to the r. So if we think about that, then what we can say is that 1 plus 1 on 3m cubed would be equal to, in this case, n is 3. So we get 3c0 x to the 0 plus 3c1 x to the 1 plus 3c2 x to the 2 plus 3c3 x cubed, and in all cases x is equal to 1 on 3m. So we can simplify that. 3c0 x to the 0 will simply be 1, plus 3c1 will be 3 times x, 1 on 3m. 3c2 will also be 3 times 1 on 3m squared. 3c3 will be 1 times 1 on 3m cubed. So if we simplify that, we'll get 1 plus 1 on m plus 3 on 3 squared m squared. So the 3's will cancel and we'll just get 1 on 3m squared plus 1 on 3 times 3 is 9 times 3 is 27m cubed. Alright, so now if I replace that up here, what we're really saying is that we want to show that 1 plus 1 on m plus 1 on 3m squared plus 1 on 27m cubed is less than 1 plus 1 on m minus 1. So these ones can cancel. If I bring the 1 on m over, we'll get 1 on 3m squared plus 1 on 27m cubed is less than 1 on m minus 1 minus 1 on m, which is less than, and if I create a common denominator, we'll get m minus 1 on m minus 1m, which is the same as less than m minus m. So we'll get 1 on m minus 1. So that's what we need to show. If we can show that, then we would have effectively shown this, which means we would have effectively shown this, which is what we're really trying to show. Alright, so if I just turn over there, to help with this, I'm going to do another substitution where I let p equal 1 on m squared. So if I start with this left-hand side of the inequality, 1 on 3m squared plus 1 on 27m cubed, we know that that will be less than 1 on 3m squared plus 1 on 27m squared. If I replace the m cubed with an m squared, I'm dividing by something smaller, so that result must be bigger. So that's true since m cubed is greater than m squared. So that means it's going to be less than 1 on 3 plus 1 on 27 times 1 on m squared. Just bring out the 1 on m squared, which means it's less than 1 on 3 plus 1 on 27 times p, because that's what we've defined p as, which means it's less than p since 1 on 3 plus 1 on 27 is less than 1. So if we're taking p and multiplying it by something less than 1, that result must be less than p. Alright, now if I think about this right-hand side, we know that m minus 1 would be less than m squared, since it's m squared minus m, so I'm taking m squared and subtracting something, so that result must be less than m squared. So if I invert them, 1 on m minus 1 must be greater than 1 on m squared, which means it's greater than p, since that's the definition of p. So what I can conclude is that 1 on 3m squared plus 1 on 27m cubed, that is less than p, and p is less than 1 on m minus 1, which means this inequality is true because p sits between them. So if you were to ignore p, you'd get the inequality that you want. So that kind of really brings us to where we can make all of our conclusions, because as I said, if we can prove this, then we can prove this, which means we can prove this. So we've now demonstrated that we can now conclude xn on xn plus 1 is less than 1 plus 1 on n minus 2 to the third. Now, if we can conclude that, we can therefore conclude, and this brings us all the way back to pretty much the beginning, we can conclude that this function is monotonic increasing, because that's the inequality we had to show. After rearranging, we get to this inequality. We've shown that it's true. Therefore, xn n minus 2 to the third is monotonic increasing. Now, because it's that and we had already shown that it was bounded above, right at the beginning we also showed that it was bounded above, it meets the two requirements of the monotone convergence theorem, so therefore we can conclude that xn n minus 2 to the third has some limit, and we call it k, and therefore, again, going back to the very beginning, the preliminary step where we showed that these two things must have the same limit, if we've proved that the limit of this function exists, we've proved that xn n minus 1 to the third has that same limit. And that is pretty much it. Now, we do also need to show that k is positive, but that's very easy to show. I mean, we can see, if I even just focus on this limit here, if we start with x3, so if we go x3, 3 minus 2 to the third, would just be x3, which we know is positive. It's equal to a half. Now, if x3 is positive and we've shown that it's monotonic increasing, then this function will always be positive, and therefore the limit that it takes being less than the bound, but not necessarily equal to that bound. We know it's bounded above. There's some limit that must be less than or possibly equal to that bound. If we know that the early value of the sequence is positive and it's always increasing, then that limit must be above 0. So that's really it. I mean, this step to work through this proof, it's almost the same, if not more, than the work required to work through step 5 in the first place and prove what we really cared about, which was the value of this limit being cubed root of 9 on 2. So you can see why I've decided to make this assumption in my original video, to then focus on the task at hand and then separately work through this proof, because this proof almost doubled the amount of effort. So hopefully you have followed that and you've seen why it was necessary. I think that I was tempted, and there probably is a temptation of many to think, well, in this question we were told that this limit existed, so can't we just assume that if this is an on bn and we know that limit exists, can't we just assume that an minus 1 on bn minus 1, that limit also exists? Why do we have to prove it? But the logic of the Stolz-Cesaro theorem says first you have to show that the limit of n goes to infinity of an minus 1 on bn minus 1. You have to show that limit exists before you can then set it equal to the limit of an on bn. So it's actually no help to us to be told that this limit already exists, because the logic doesn't work in reverse. So we had to prove that this exists before we can then make them equal. So actually all of this would have been avoided if the question had said assume that limit exists, and actually if they had told us that, they would have given a very good hint at the use of the Stolz-Cesaro theorem, which probably would have made this question a bit more obvious in terms of what you had to do. But nonetheless, we got there anyway, so we've done all the work to prove this value. Now we've done all the extra work to validate our assumption and make sure it was robust. So that's a wrap on this question. Definitely the hardest high school math question I've ever come across. We'll see if one day some student sends me another one that's even harder, but definitely at this point, very difficult question. And remembering that there were only 2 marks on offer for all of this work plus all the work I did in the prior video, it just really is quite baffling how students would be expected to tackle this in a time-limited exam. But there you have it. There's all the steps. We've used the monotone convergence theorem, something, again, I'm not sure is in a high school syllabus, but hopefully it all makes sense to you. It's been quite a lot of, I guess, interesting steps. Proving this might not have been an obvious thing to most people, but it did come in handy, because we've essentially proven the inequality by taking a different inequality and then kind of getting there in multiple steps. And using this induction, I think induction is something that high school students might gravitate to naturally, but often it's at this step 3 where things can get tricky. And thinking to create this function and generate a recurrence relationship, and then from there create another function, and then think of getting that function of 1 on j to then help you eventually get to where you have to get to. Again, I just can't see a lot of high school students making all those logical leaps. But nonetheless, hopefully all of these steps you were able to follow along, even if you might not have thought of them yourself. So there it is, and tick boom.